Hey everyone. If you're into geology, mineral exploration, or just curious how the earth concentrates something as valuable as gold, you're in the right place. In this video, we are going to explore a simple but powerful framework that helps geologists understand and predict how gold deposits form. It's called Source Transport Trap Model, or STT for short. This model helps us answer three big questions. Where did the gold come from? How did it move through the crust? And why did it stop and pile up in one spot to form a mineable deposits? Okay, let's jump in and unpack how these three components, source, transport, and trap, work together to form the world's richest gold deposits. The biggest gold deposits tend to occur when a large gold source, efficient transport pathway, and effective trapping mechanism coincide in time and space. So I will break down the STT model into its three components and discuss how each operates in gold depositing system. This is a schematic representation of the original mineral system concept, showing a broader range of model, including energy, ligand, source transport, trap, and outflow. And my focus in this presentation would be the source, transport, and trap. And this is the casting of conceptual model in a spatial context in the crust. I will then illustrate these concepts with real-world examples from Canadian gold camps and deposits such as Red Lake, the Abitibi Greenstone Belt, Hemlo, and we'll examine how source transport trap processes manifested in each case. So the goal is here to provide an informative, technically rigorous, yet accessible overview for audiences with geoscience background, bridging academic concepts and industry examples. So in the STT model, the source represents where and how gold and associated elements are derived and mobilized. Gold in the Earth's crust typically exists in trace amounts within common rocks and minerals. The geological process is required to liberate and concentrate it into ore-forming fluids. So key source mechanism for gold includes metamorphic fluids, magmatic fluids, or remobilized sulfide melt. So let's start with metamorphic devolatilization, metamorphic fluids. So it's the most common and accepted fluid source for gold. In many gold deposits, especially orogenic gold, in metamorphic belts, gold-bearing fluids are generated by metamorphic reactions at depths. During prograde metamorphism, for example, from green schist to amphibolite facies, dehydration of hydrous mineral releases carbon dioxide and water fluids that carrying gold and other metals. And these fluids leach gold from broad volumes of rocks. Okay, this is generalized fluid release curves for a shale here in the left panel along a 30 degrees C per kilometer geotherm. Water release is continuous with increasing pressure and temperature because of the complex crystalline solid solutions constituting pelitic rocks that progressively break down by continuous reactions. Changes in the slope of the release curve are related to beginning and completion of dehydration of major hydrosilicates. And the right panel here is assuming rock is initially dry and then hydrates to a zeolite facies assemblages with 5% weight percent of water. And depending on the exact composition of the system, especially the remaining water concentration, partial melting may begin somewhere near 700 degrees C to form migmatites. The example of this fluid source type in Canadian goldfield is in Arcan greenstone belts like the Abitibi or Red Lake districts. Metamorphic devolatilization of greenstone basalts and sediments is believed to have produced gold-rich water, carbon dioxide fluids that fed the gold systems. And such fluids are often carbon dioxide rich and low salinity, consistent with a deep crustal metamorphic origin. In the right diagram, here Pitkin measured gold in the different metamorphic facies of the metasedimentary rocks. And this diagram showed a significant decrease in gold that has been released from the rocks as metamorphism progressed. So in other words, it shows that more gold is released from the metasedimentary rocks by prograde metamorphism. And the important implication is that in the Abitibi greenstone belt, 10 tons of gold mobilized from 1 cubic kilometer sedimentary rocks during prograde metamorphism to sillimanite metamorphic zone. And world-class gold deposits in the area host about 7,500 tons, which is about 3% of total gold mobilized from the sedimentary rocks with a volume of 25,000 cubic kilometers. And this highlights the significance of metamorphic devolatilization. This is another example for the metamorphic devolatilization of mafic rocks. Here, left panel here shows minor changes in gold content from sub-green schist to upper green schist, only about 1 ppb, and then significant drop in the gold from metavolcanics in the amphibolite facies, about 0.2 ppb. The same as previous example, gold has been lost or released from the host rock during metamorphism and potentially led to the accumulation and deposition of gold deposits in the region. Now let's move on to the magmatic fluids. In some cases, magmatic hydrothermal processes act as the source. Cooling plutons or porphyries exsolve magmatic fluids that can carry gold, typically in water salt mixtures. And this is common for epithermal and porphyry deposits. For example, the Bruce Jack gold silver deposit in BC formed in a Jurassic Island rock setting and is interpreted as porphyry related and intermediate sulfidation epithermal, meaning gold was sourced from magmatic fluids released by nearby intrusive bodies. And these magmatic fluids, rich in water and carbon dioxide, sulfur, and metals, ascended into the shallow crust to form the high-grade vein system at Bruce Jack. Similarly, in the Abitibi, certain deposits, for example, Canadian Malartic or part of the Kirkland Lake camps, have been interpreted to involve a magmatic contribution, an oxidized monzodiorite intrusion at mid-crustal depths, exsolving gold-bearing fluids, something like that. However, distinguishing of magmatic fluids from metamorphic fluid sources in many gold camps remains an area of debates, as many of you have seen the paper by Goldfarb and Pitkin in 2023. So I would like to point out here is that the fluid source in orogenic systems can be both metamorphic and magmatic fluids. The consensus for most orogenic mesothermal gold deposits is a supracrustal metamorphic fluid source. Goldfarb and Pitkin 2023 note that the majority of world-class orogenic gold deposits formed at depths of around 6 to 12 kilometers. This is mesozonal, where fluids are dominantly metamorphic. Direct magmatic fluids input at those depths is considered unlikely, according to them, or very diffuse. Instead, large-scale metamorphic events during regional compression and crustal thickening can liberate gold-bearing fluids from extensive rock volumes. In Red Lake, for example, the main gold mineralization occurred syntectonically during regional metamorphism and magmatism, suggesting metamorphic fluids with possible minor magmatic input as a source. So the ore fluids at Red Lake are carbon dioxide dominated with very little water. Chi et al. In 2006 proposed could reflect high-grade metamorphic origins in the lower crust, perhaps involving granulitization that drives off water and enriches carbon dioxide. And they also note that early degassing of the deep carbon dioxide-rich magmatic intrusion is an alternative source for Red Lake's unusual fluid composition, underscoring that source interpretations can be really complex. Anyway, let's move on the other gold sources. In some cases, gold may be sourced from specific rock units that are unusually enriched. For example, banded iron formation or carbonaceous shales can be primary gold reservoirs that release gold during metamorphism. The Hemlo deposit in Ontario is hosted in sedimentary sequence with abundant sulfide. Additionally, deeply circulating meteoric water can leach gold from broad areas of rocks. Ultimately, any effective gold deposit requires a large metal source, either a voluminous package of crustal rocks undergoing metamorphic dehydration or a sizable magmatic hydrothermal system to supply enough gold into the ore-forming fluids. Before moving on from source to transport, let's talk about the importance of gold bisulfide complex in gold solubility. So this figure is from Gabori 2019, is a log FO2 pH diagram showing the solubility contours of gold bisulfide complexes in hydrothermal fluids, and it illustrates how variation in redox condition and pH influence gold solubility and precipitation in orogenic gold system. So what we have here is that gold solubility is maximized here at near neutral pH around 7, and also at intermediate redox state just below sulfate fence, where actually pyrite is stable, but sulfate has not yet formed. And these arrows, the white arrow shows increasing FO2 and gray arrow shows decreasing FO2, shows a deviation from the optimal redox range. Both arrows decrease gold solubility, triggering precipitation. Black arrows is changes in pH, show that moving toward more acidic or more alkaline pH also reduce solubility, again favoring precipitation. So the implication for gold precipitation from this diagram actually is that the diagram explains why orogenic gold deposits often form when fluids acidify, for example, by losing carbon dioxide during fluid immiscibility, or oxidize or reduce, for example, through mixing with other fluids or fluid rock interaction. Also, the hydrogen sulfide, because it's a dominant ligand transporting gold, its consumption, for example, by pyrite precipitation, will also drive gold precipitation. So why it matters? This diagram is a conceptual key to understanding where and why gold drops out of solution in hydrothermal system. It shows that gold precipitation is highly sensitive to small changes in physiochemical environment, especially pH, redox conditions, or availability of ligands like hydrogen sulfide. And this helps exploration geologists and mineralogists predict the most favorable zones in a fault fluid system for gold deposition. This is also, I thought, might be interesting to discuss. This figure argues against a purely magmatic or mantle source for gold. It's from Gangi et al. 2016, shows a plot of delta 33 sulfur versus delta 34 values from pyrite in hydrothermal gold mineralization of Shaban Fairview mines alongside a large data set of sulfur isotopes data from various rock types across Barberton Greenstone Belt in South Africa. What it shows actually is these are pyrite grains from Sheba and Fairview. They got delta 33 sulfur values between around minus 0.5 and 1 per mil, and 34 sulfur value is between around 0.8 to around 10 or 9. So these values overlap and cluster near highest density region of entire Barberton Greenstone Belt sulfur isotope data, which is from sedimentary and volcanic rocks, especially at delta 33 sulfur of 0 and delta 34 sulfur of around 1.5, somewhere around here. So what that means here, the delta 33 is not 0, so that indicates mass independent fractionation of sulfur, a signature of sulfur process in noxic arcane atmosphere. And the Barberton Greenstone Belt host rocks, actually particularly sedimentary units, for example, shale or chert, carry this atmospheric mass independent fractionation of sulfur signature. Therefore, the sulfur in pyrite in the gold deposits likely came from these atmospheric processed sediments, not directly from a deep mantle or magmatic source. So the gold transport requires sulfur. Gold is transported in hydrothermal fluids primarily as hydrosulfide complexes. And these complexes require available sulfur in solution to stabilize gold in transport. And the implications from this figure is that since the sulfur has a clear atmospheric mass-independent fractionation signature, the fluids that carried gold must have leached sulfur from surface-derived rocks, especially those bearing diagnostic pyrite or barytes. Therefore, sulfur was essential not only for gold transport, but also diagnostic of source rocks. So I can say that this figure argues against a purely magmatic or mantle source for gold, which would yield sulfur with delta 33 of 0, mass dependent only. Instead, it supports a crustal source model where deep hydrothermal fluids acquired gold and sulfur by interacting with the volcanic sedimentary volcanic successions. To sum up, the source components of STT model entails both the provenance of the gold, metals liberated from crustal rocks, and the genesis of the gold carrying fluid. Organic gold deposits typically tap metamorphic fluid sources in mid to lower crust, whereas epithermal and intrusion-related deposits rely on magmatic or near-surface hydrothermal sources. In either case, gold is dissolved in the fluids as chemical complexes, such as gold bisulfide complexes in reduced metamorphic fluids or gold chloride complexes in magmatic fluids, enabling its journey upward. So in summary, you can say that source of fluids and generally also the metals and metal binding ligands are generally thought to come from metamorphic devolatilization reactions, typically as rocks move into green schist to amphibolite facies, and devolatilization of metavolcanics, also a potential source of gold and fluids, and role of magmatic fluids and deep circulating meteoric water also remain debated or not clear. Let's move on now on the gold journey in transporting and finally trapping, where the journey actually ends. Transport refers to the movement of the metal-bearing fluids from the source region to the site of deposition. In hydrothermal gold systems, transport is accomplished by hot aqueous fluids, plus minus carbon dioxide, migrating through the Earth's crust. And two major aspects of transport are, first, the pathways or conduits that fluids travel along, and second, the mechanisms that keep gold dissolved during the transport. So let's start with the structural pathways. Fractures, faults, shear zones, and porous rocks units are critical in channelizing hydrothermal fluids. In fact, rock structure is a primary control of the orogenic gold mineralization at all the scales, as it controls both the transport and deposition of fluids. Large crustal scale fault zones often serve as the main plumbing for gold-bearing fluids in orogenic belts. Another example from Canadian goldfield is in Abitibi's belt, which is the richest gold camps, is the gold line with major faults like the Porcupine Ester or Larder Lake Cadillac deformation zones, fault zones, which acted as a long-lived fluid highways tapping deep sources. In Red Lake Camp, we'll talk in more detail in my next video. Regional D2 shear structures trending east-southeast formed during the ocean orogeny and focused fluids into the Kochener-Balmertown mine trend, where the giant Campbell Red Lake deposit formed. Fluids there were focused along discrete structures and not diluted by surrounding rocks. But how does the fluid transport through the crustal scale fault zones? The widely accepted model is fault valve model. Okay, this is a fault valve model explained by Nassif et al. 2022. We have three panels here, three stages. Here we have upper cross orbital ductile transition zone, or BDT. Stage 1 is below BDT. We have lithostatic regime. What's happening here is fluid pressure exceeds lithostatic pressure. Then we have fault valve failure, which is actually a pressure release, and then rapid pressure drop, flash vaporization, and phase separation. So what's happening here is metamorphic fluids accumulate beneath the low permeability barrier, and rupture opens extensional fractures in the fault fracture mesh, and carbon dioxide water fluids separate, and gold solubility drops. So the results of this stage is blocky interlocking quartz that grows in open veins. Quartz traps early fluid inclusions, and actually the pressure condition here is supra lithostatic or lithostatic. Okay, let's move into stage 2, which happens at the BDT, the transition zone. It's a pressure cycling. So in stage 1, we have lithostatic regime. Stage 2 is pressure cycling, and stage 3 in hydrostatic regime. So in stage 2, we have gold precipitation via sulfidation, quartz recrystallization, fracture resealing by pressure rebuilding. So sulfides such as pyrite, arsenopyrite form in reopened veins and grain boundaries. Microscopic gold inclusion occur within sulfides, and early quartz is deformed, dissolves, and fine polycrystalline aggregates would form, and new fluid influx begins next overpressure cycle. So the results here is the evidence of reopening, recrystallization, pressure cycling, and fluid inclusions that show post-entrapment modification. In independent 3, above the brittle ductile transition and the regime here, hydrostatic regime, as we discussed, is a final decompression that we have native gold precipitation. Fault fracture mesh now lies in brittle upper crust near hydrostatic pressure, and fluids flow freely and there's no pressure buildup. So the results is actually a coarse native gold along quartz grain boundaries, fractures, and clear quartz or calcite grows in open spaces. One of the examples here I can make is Bruce Jack's epithermal vein, for example, formed in a highly fractured, brachiated zone adjacent to porphyry intrusions. So open space fractures and breccias permitted rapid upward fluid flow and periodic pressure release. This periodic pressure release, we can call it boiling, which happens in the shallow environment. Over time, continued deformation can keep fractures opening and closing. So this opening and closing of fractures is called seismic pumping. And then these seismic pumping draw fluids upward from depths. So in summary, without effective transport conduits, even gold-rich fluids may never reach a site where it can form a deposit. On the chemical transport mechanism, while moving through the crust, the hydrothermal fluids must keep gold in solution until deposition. So gold has low solubility in pure water. It travels dissolved as complexes with ligands like sulfur or chlorine. We talked about that already. Common gold complexes includes gold bisulfide, introduced sulfur-rich fluids, and gold chloride in oxidized saline fluids, for example. In metamorphic organic systems, fluids are typically water, carbon dioxide with low salinity and an elevated H2S. So gold is transported primarily as gold sulfide complexes, often stabilized by carbon dioxide or maybe methane. In contrast, magmatic fluids like those we already made some examples, may be richer in chlorine and undergo boiling, carrying gold as chloride or bisulfide complexes, depending on the oxidation states. And the presence of other elements such as tellurium or arsenic, which can form complexes with gold, also enhances transport. Notably, sulfur is a critical ingredient. Most gold deposits are associated with sulfide minerals, indicating that sulfur-bearing complexes carried and then released the gold. In summary, transport in gold systems involves structural plumbing, faults, fractures, and chemical vehicles, such as complexes or mills keeping gold mobile. A highly efficient transport stage is one where large volumes of gold-bearing fluids are focused through structures with minimal loss of gold in a road. The final fate of that gold depends on encountering the right trap, as discussed next. So the trap is a set of conditions, physical, chemical, structural, that cause the traveling gold to precipitate and concentrate into an ore deposit. Essentially, a trap is where the gold-bearing fluids can no longer return gold in solution, so the gold drops out and accumulates. Several key trapping mechanisms operate in gold system and often simultaneously. So let's start with the structural traps. So changes in the geometry and mechanics of the conduit can create traps. When a fluid-filled fault or fracture undergoes a pressure drop, for example, at a bend, jog, or fault intersection that creates dilation, the sudden drop in fluid pressure can cause gold to precipitate as the solubility of gold decreases with drop in pressure for bisulfide complexes. So orogenic gold deposits are famously structurally controlled, with golds often occurring at fault bends or fold hinges or intersection zones that acted as traps. For the chemical trap, we actually already talked about this, but gold will precipitate if the chemical condition of the fluids change such that the gold complexes break down. One common mechanism is sulfidation of wall rocks. When a gold bisulfide fluid interacts with iron-rich host rocks, it can form iron sulfides such as pyrite or arsenopyrites, thereby stripping sulfur from the fluids and destabilizing the gold hydrogen sulfide complex. And the gold then drops out with the newly formed sulfides. So many gold deposits show this phenomenon. For example, at Hemlo, the gold is intimately associated with arsenopyrite and other sulfides replacing host rocks. The deposit's host sequence included iron-rich sediment. An introduction of the sulfur-rich fluids caused abundant arsenopyrite, pyrrhotite, and molybdenite to form, with gold included in the assemblage. So the later metamorphic melting of this assemblage then reconcentrated gold into new sites. But the initial trap was likely chemical sulfidation of iron-bearing rocks. Another chemical trap we can talk about is fluid mixing. So when two fluid mix, a dip hot gold-bearing fluids with cooler, for example, oxidizing meteoric water, the changes in temperature, pH, and redox condition can destabilize gold complexes, gold to precipitate. For instance, in epithermal systems like Brucejack in BC, the infiltration of cooler meteoric water into magmatic fluids not only cooled the fluids but also likely raised its pH and causing gold and silver to precipitate. The next one is boiling and degassing. So in shallow environments, epithermal deposits, for example, at depths of less than 1 to 2 kilometers, boiling of the hydrothermal fluids is a potent trap. When a fluid boils, it loses volatile components such as carbon dioxide into the vapor phase, and the liquid's capacity to carry gold drops dramatically. Gold and other metals then precipitate from the liquid. Boiling also causes rapid precipitation of quartz and some other minerals, forming classic epithermal vein textures. In summary, a trap is any phenomenon that concentrates gold by precipitating it from solution. Physical traps create space for large volumes of fluids to dump their load, a vein in a fault jog, for example, while chemical traps, all of them trigger precipitation at a molecular level, fluid cooling, mixing, or reacting with host rocks. The richest gold deposits often reflects highly effective trapping, a combination of structural focusing and chemical triggers that cause almost instantaneous gold deposition from large volumes of fluid. Now let's have a look at some examples of structurally controlled transport and trap models from regional to local scale. First, I would like to make an example from Barberton in South Africa, Barberton Greenstone Belt, and then from Red Lake in Canada. So what you can see here is the refolded syncline geometry of Barberton Sheba Fairview complex SFC gold system. It visualizes how regional scale fluids flow becomes focused into ore controlling structures, leading to high grade gold mineralization. So here, what we have here is the regional fluid transport mechanisms, bedding parallel fluid flow along shale graywacke contacts and bedding planes in folded sedimentary sequences, and this flow is enhanced by flexural slip during folding, a process shown in the figure by curved bedding planes and arrows indicating lateral fluid movements into the fold hinges. These pathways act like fluid highways, much like the large scale shear zones, the Red Lakes, due to structures of the Porcupine-Dexter Fault in Abitibi, as we already discussed and we'll discuss also next. This figure shows how extensive bedding parallel fluid flow develops during progressive deformation, matching the idea that without these pathways, fluids cannot reach sites of mineralization. This figure is from Dobey et al. 2002. It shows a schematic structural evolution model for Campbell Red Lake gold deposits during progressive D2 deformation. This figure elegantly illustrates both transport mechanism, how fluids move into a zone, and trap mechanism, for example, how structures cause gold to precipitate and concentrate. We have three panels here. Panel A is early D2A stage, initiation of transport pathways. Here folding begins northeast to southwest. Shortening actually produces upright F2A folds in metavolcanic units, and veins initiates then, and we have axial planar fissures, vein, and oblique discordant quartz veins formed during this early folding. These early veins represent the first generation of fluids conduits exploiting dilation zones created during the dilation zone that created during folding. The next stage is late D2A. Fluid flow intensifies here and trap forms. We have transposition and boudinage, boudin necks and fold hinges create open space ideal for fluids ingress, and vein thickening and dilation occurs at these localized structural positions. We have high strain zones acts as highways conducting and focusing fluids like major crustal scale shear zones in Abitibi, and boudin necks and fold hinges form mechanical and geometric dilation zones leading to pressure drops and gold precipitation, exactly as we already described it earlier. Here we have D2B stage. It's late revoking and vein localization. We have reverse sinistral shears like the Campbell fault develop, reactivating or cross-cutting earlier structures. These act as late-stage fluid conduits and remobilize or focus mineralization into preferred zones. If we want to talk about relation to seismic pumping and shoots, so we have repeated deformation causes here fractures to open and close, so enhancing episodic fluid flow, as we already explained it as seismic pumping. And at intersections of earlier and later structures, fluid traps concentrate high-grade shoots akin to Red Lake's high-grade zone or Doris's hinge zones. So in conclusion, the source transport trap model is a powerful conceptual tool to dissect the formation of gold deposits by examining each component, for example, source, the origin of golds and fluids, then transport, the pathways and processes moving gold-bearing fluids, and finally trap, the conditions that precipitate and concentrate gold. We can gain a structural understanding of why a deposit formed where it did. For both industry and research, thinking in terms of STT helps predict where undiscovered gold might be. For example, if one can identify a potential source area, say a particular stratigraphic unit or intrusion known to generate gold-rich fluids, one can then look for connected structures that could transport these fluids and along those structures, and to search for likely trapping sites, bends, lithological contacts, etc. and that would dramatically improve the gold exploration strategies. Having outlined the general STT model here, in the next video, I will turn to specific Canadian gold deposits and districts to illustrate these concepts in real geological setting, and each example will highlight how source, transport, and trap factors actually contributed to the formation of that specific deposit.